of the introduction. Well, okay. Well, hello everyone. Welcome to the centenary of the introduction of combinators. We're hoping to celebrate this this is exactly 100 years after the talk that was given by Moses Scheinfinkel in the building that there's a copy of behind me here. So I myself have been kind of a combinator enthusiast for about 40 years now. I don't believe I've ever talked about combinators in public before. And this is a particularly daunting way to do it because we have with us essentially all of the very large fraction of the world's experts on combinators. I think this is kind of channeling what it might have been like for Moses Scheinfinkel back 100 years ago on December 7th, 1920, as the Göttingen Mathematical Society got started, because probably sitting in the front row was David Hilbert, kind of the most prominent mathematician in Göttingen and perhaps worldwide at the time, ready to comment on Moses Scheinfinkel's talk. So I'm kind of channeling that feeling here. So what we're going to do is I'm going to talk a bit about combinators, explain a bit about what they are, their significance, some things we now know about them 100 years after they were first announced. Then when I'm done, we'll kind of turn it over to Q&A and discussion with our combinator experts and others. So, and by the way, I've since this event has been set up, I've been getting a big stream of interesting pointers from combinator experts saying, there's this interesting thing about combinators, that interesting thing. I'm not going to mention all of these things, but hopefully people will have a chance to do that afterwards. So what's the big picture of combinators? I would say that the event that we're celebrating here was kind of the seed that we can see led to the idea of universal computation, which has led to basically the possibility of computer technology, the idea of software, a lot of modern technology, and as we're now seeing, a lot of science that can be done, although that's something that's only emerging in very recent times. So it was a big deal. The seed that was sown was a big deal. It was also very hard to understand. The things that were said probably at Moses Scheinfinkel's talk were probably understood by the significance was understood by almost nobody at the time. Combinators have remained this kind of thing, which is a seed, an interesting thing, a footnote. What I want to do here is tell you about combinators and about why maybe they shouldn't be quite so much of a footnote. All right, let me go ahead and first of all, okay, so this is the chap who gave that talk 100 years ago now, Moses Scheinfinkel. This is a picture of him taken probably in the year after that talk was given. And the talk that he gave was entitled Elements of Logic, or Elemental der Logik. I can't do the German, sorry. We're not going to get that level of authenticity here. About 4 years later, paper appeared that was a summary of that talk. And so maybe what I should do is start off telling you what that paper said, and then I'll tell you about what Moses Scheinfinkel introduced and kind of how this all works. So here's an English translation of the beginning of this paper. It is in the spirit of the axiomatic method, as it has now received recognition, chiefly through the work of Hilbert, who might have been sitting in the front row, that we not only strive to keep the axioms as few and their content as limited as possible, but also attempt to make the number of fundamental undefined notions as small as we can. We do this by seeking out those notions from which we shall best be able to construct all other notions of the branch of science in question. Well, so then he starts off and says, as is well known, the fundamental propositional connectives of mathematical logic, which we reproduce here in the notation of Hilbert, are these. So what he's doing here is to say this is what people build logic out of, not or, and, implies, what is that one, equivalence. So we're used to the idea, and people knew it at the time, that logic can be built out of those kinds of primitive notions. What had happened, and what Schoenfinkel goes on to say, that the reduction to a single fundamental connective is nevertheless entirely possible. And this was discovered not long ago, he says, by Scheffer. Actually, it was discovered before Scheffer by Peirce and other people. But what was it that was discovered? So we can represent standard logic by ands and ors and nots, but there's another possibility that was discovered, and that possibility is that we can also represent logic with a single operation, NAND. And what Scheffer showed, and in fact, Schoenfinkel reproduces this result on the next page of his paper, is that using the single connective NAND, you can generate all of the standard operations of logic. So for example, AND is P NAND Q, NAND P NAND Q. And what's some other examples here? Implies is P NAND Q, NAND P, and so on. So in other words, we can take what we thought of as something that was a kind of the basics of logic, and or not, and we can make it even simpler. We can represent logic in terms of just a single operation NAND. Okay, and so back in the day, Henry Scheffer had written a paper about that, and one might have said, who cares? This is some very obscure feature of logic that it's possible to reproduce all of these logical expressions just in terms of NAND. You might say, who cares? And perhaps for about 40 years or so after that was discovered, it was correct, who cares? Well, now there's a quintillion versions of this that exist in the world, because basically every piece of, every microprocessor, every logic circuit is built using metal oxide semiconductors using NAND. So this thing that started as this obscure piece of mathematical logic, this obscure kind of reduction of logic into just NAND, turned out to be extremely technologically significant. And as I say, there's now a quintillion NANDs that are probably running right at this moment around the world in computers. Okay, so that was sort of Schoenfinkel's inspiration for what he did, was the idea that basic logic with ands and ors and nots could be reduced to just this single operation of NAND. So then he asks, he says, the successes we've encountered thus far encourage us to attempt further progress. We're led to the idea, which at first glance certainly appears extremely bold, of attempting to eliminate by suitable reduction the remaining fundamental notions. Those are propositions, propositional functions, and variables from all the contexts that we're dealing with. And then he says, then he goes on to say, and this is kind of the big sentence of his paper. Let's go back to his paper here. The big sentence, I think it appears on page 2, if I can get this. Yes, there we go. Is to say that that's okay. He says that this reduction of removing all of these kinds of notions, he says, it's remarkable to me in the extreme that the goal we've just set of removing all of these kinds of notions can be realized. Also, as it happens, it can be done by a reduction to 3 fundamental signs. So that was kind of the main thing that Schoenfinkel was talking about. Can you take all of these constructs that exist in defining mathematics and mathematical logic and reduce them to something simpler, as Scheffer had reduced standard logic to something simpler in the form of NAND? Okay. So the question is, what did Schoenfinkel actually do? So the basic idea that he started with was, we've got these expressions that appear in mathematical logic. They're things that say for all x, this is true, that's true, etc., etc., etc. How can we break that down? How can we find a uniform way to represent all of those kinds of constructs? And what he realized is what we would now say is that everything that you write like that can be written as a kind of symbolic expression. At the time, he didn't have kind of the language to describe that, but that's basically what he was saying. So in modern times, what we would say is something like, we have some simple piece of, let's say, some mathematical kind of thing, and we know that in fact we can represent that thing, which looks like a piece of math, in some very uniform way, just saying it's power of x and 2, etc., 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 plus. Or we could say we could represent that whole thing as a tree, where we're just saying there's a plus at the top and then there's some powers that represent these kinds of things. And so what Schoenfinkel's first big sort of realization was everything you can write down as a kind of mathematical expression or a statement in mathematical logic can be represented in this kind of way that we would now say it's like a symbolic expression. And in a sense, what he said was, okay, we've got this thing, but there are things here like power and plus and so on. Those are things that, in a sense, are just features of the way that we are giving meaning to this kind of construct. But there's a raw construct. There's just the pure tree that exists here. It's a little bit like in ordinary logic when we say P and Q, and that's kind of a symbolic P and a symbolic Q. Later on, we're going to say P means it's raining today, Q means I have an umbrella, and so on. We're going to give meaning to these things by sort of feeding that in from the outside. But what we have at the beginning is just the pure structure. So what he realized, and it was kind of a big thing to realize, is that you could represent all of these kind of mathematical statements in the form of what we would now call symbolic expressions. And those symbolic expressions could be represented in some sort of raw form just in terms of structure, in terms of some kind of tree-like structure. And then from the outside would come all the things that you would feed in, like the pluses and powers and twos and so on, that would give meaning to it. Okay, so then what did he actually invent? Well, so he invented these things, these combinators, and we can write them out in modern form here. And it's the fact that it's really easy to write these things out in Wolfram language is kind of might be a clue as to why I've been interested in these things for a long time. But that's what Schoenfinkel came up with, the S combinator and the K combinator. What are these things? These things can be thought of as kind of tree representing kinds of constructs. Okay, how does that work? Well, let's say we have something like this. We make up a big collection of S's and K's. There it is. This on its own does absolutely nothing. But what we can say is, let's imagine that we just feed in some specific variables here. Let's say A, B, and C, and we just say, let's use these rules that we have that define what S with 3 things after it and K with 2 things after it mean. Let's just use those rules and see what happens. Okay, so we got out of that this A of B of A of C. We can say what's the tree form of that. What we did, oh, that wasn't very exciting. I should have done it a different way. But anyway, what we did there was we constructed this expression. What we've got is this kind of raw combinator object that basically says, given that you feed in these particular objects, construct something like this. So that was kind of the big idea, that just from those kind of primitives, you could construct anything. Now, how does this actually work? Well, it's a little bit hard to see what's going on here. Let me try and show you a better picture of that. Okay, so here's another version of that. Oops, move this out of the way. Here's another version of that, showing the series of reductions that are being made, each time applying one of those S rules or the K rule. Here's a slightly better version of that. Every time there's a red thing here, it's applying the S rule. A blue thing, it's applying the K rule. We start off from that thing at the beginning, and we end up at the end with the result that we wanted there. So it's a very bizarre thing that we can break down any of these kind of tree construction operations just into some combination of S's and K's. Okay, so but so what? What can we really do with this? Well, the thing that Schoenfinkel realized is that you can use this to essentially, as we would now say, compute things. What can you compute? Well, for instance, one thing you can compute is the operations of ordinary logic. You can say, let's say I'm feeding in a couple of variables that I want to generate, and you can say, let me create a combinator expression that will do that. Now, in order to do this, we have to do something else, which is we have to say, how are we going to represent true and false just in terms of combinators? How are we going to start representing everything in terms of combinators? Today, it's not quite as surprising we can do this because we're used to kind of the idea of computation and the idea that we have computers and we can represent everything as a kind of as a sort of computational structure inside a computer. But then it was, I think, not obvious at all. But in this particular case, we can say, let's take true to be, oh, that's a bizarre form of true. That's not right. That's not right either. Something went wrong with this. I should regenerate this. Let's take false to be just to be S of K and true to be K. Then these things here, and I thought that this was generated correctly. This should be the minimum. No, these are wrong. Well, we can redo it. But these should be the minimal expressions you need with S of K of true is true and K is false, of being able to basically compute the operations of Boolean algebra. So the question is, what else can you compute this way? Well, for instance, another thing you can compute, let me pull that up, is let's say you want to do arithmetic. Well, then you have to have some representation for numbers. And one way you can represent numbers is basically just by nested S of S of S of S of S n times to represent the number n. And if you do that, you can again, let me see here. You should be able to again generate. Let's see if I have this here. You should be able to generate. So like say, for example, this is what you can get if you want to oops, there we go. Let's say you are going to this is the addition of 1 and 2, where those things are represented by nested collections of combinators. Or for example, it gets a bit more complicated. You can go and you can do the same kind of thing. You can make a combinator that in that representation of numbers does multiplication. So there's that's the combinator that does that. And then you can say, this is the series of steps that you get by using that reduction rule for doing multiplication of 3 by 2. So this looks like kind of a crazy way to do things, but the most important thing is that you can go and compute. You can compute any kind of thing in this way. So, for example, there's the computation of power. There's the combinator for computing power with that representation of numbers and so on. And if we go on, we can get to here's a combinator that represents a single step in the evolution of the Rule 110 cellular automaton, which we know is computation universal. So if nothing else, having this combinator, it's a big, complicated, messy thing. This is a program written in combinators that reproduces the Rule 110 cellular automaton. And we can go ahead if we want to, we could run it. That's just a picture of from my New Kind of Science book from 18 years ago now, of that combinator running to do the operations of the Rule 110 cellular automaton. Okay, so that's kind of the idea of combinators. we've got these two operations, these two things, S and K. We combine them. That's our kind of low-level machine code. With that low-level machine code, we're able to create things that will be able to construct any symbolic expression and then do, in the end, any computation. It wasn't obvious at the time that Schoenfinkel was around what on earth it might mean to do any computation. What he imagined was he was just trying to reproduce the objects in mathematical logic. Okay, but given that we have this idea of these S and K combinators, we can ask, what do these things do? If you just look at them kind of in the wild, you just look at S and K combinators on their own, what do they typically do? Well, so we can enumerate possible combinator expressions. Those are ones with three elements, and we can say, what do these do? Well, first thing we can do is just run them and see what happens. And what we find is that this is what happens with a few of those expressions. We just see after a few steps, they end up at a fixed point where they just have some collection of combinators to which the combinator rules no longer apply. Things just stop. We can just figure out, okay, that's the distribution of essentially halting times of how long it takes this combinator reduction to stop. But by the way, I just want to say that what I want to do here is I'm going to talk a bit about kind of combinators in the wild, combinators and how they behave. Then I'm going to talk a little bit about the context of combinators in terms of the history of mathematics and computation. And then I'm going to talk about Moses Schoenfinkel himself and what we now know, the things we've now pieced together actually just in the last few weeks or a month about Moses Schoenfinkel. So, okay, first question is, what do combinators do in the wild? And the answer is, most combinators in the wild just run for a little while and then halt. By the way, for combinator experts, what I'm talking about right now is mostly leftmost, outermost evaluation. We'll talk about other things later. So that's the halting time distribution, I think, for size 6 combinator expressions. But then what happens is, as we get to, we can ask, well, what else can happen here? Okay, so the first really surprising thing that happens is when we get to size 7, we find this combinator expression here. And if we try running it, what happens? Well, the answer is it never goes to a fixed point. Instead, we just get bigger and bigger and bigger combinator objects. So here's the plot of what happens as a function of number of steps. This is the size of that S combinator expression as a function of number of steps. So this is the first non-halting combinator expression. So most of the time we just say, okay, we're doing these combinators, they're doing computation, they get a result, that's the end of it. But when we get to this size 7 one, for the first time we have one that doesn't halt. And if we look, what does this do? Let's look at, let's say, the ratios of successive sizes on successive steps. And it's pretty weird that something as simple as the thing I just showed can make something that complicated, but we haven't kind of seen anything yet. If we look at, well, that's the distribution of halting times for the ones that do halt. We can keep going. We can say, what's the distribution of the time it takes for the combinator to halt versus the size of object that it builds versus the size of symbolic expression that the combinator builds. That's the result. So for example, here there's an expression that takes a certain number of steps to halt, but these all come from, I think these are all size 7 combinator expressions. This is a tiny little combinator expression, but it builds a pretty big thing here. So, oh, I guess I don't have the examples here with oh, maybe I have some. Okay, so this is that's a typical example of what happens. That's a tiny, I think that's a size 7 combinator expression. Unfortunately, I didn't label it properly here. This starts from that size. It runs for some number of steps, and then it halts at that size there. Here's another example. This is now running for what, 50-something steps. That's the combinator expression, and then it halts. There's another one, runs for a few more steps, then it halts. Sometimes these things can run for quite a while. That's one that runs for 300 and something steps before it halts. And again, it's all of these are very tiny programs doing rather complicated things. Sometimes you get nice nested patterns. Here's one that produces a nested looking pattern. That one halts after 21,720 steps. Sometimes you get something that's more like growth. That's one that shows very regular growth. It just grows like square root of time, square root of number of steps. But if you look, for example, this is the collection of different kinds of things that can happen with size 8 combinator expressions, just looking at the ratio of the successive sizes. So it's kind of remarkable. You might think it's kind of remarkable that something this tiny could produce so much complexity in its behavior. Well, you can keep going. You can look at all kinds of different things. Sometimes they look like they're going to do complicated things for a while, and then they get simple again. Here's one that goes for, how long does this one go for? This one I think goes forever. If you look at what is it doing, it's producing something that's kind of like an integer exponent function, counting the number of zeros in a number and so on. Anyway, you keep going, you see all kinds of different things happen. Sometimes it looks as if one's going to get really sort of complicated random behavior, but after a while things stabilize and all looks good. Sometimes you get, sometimes you can ask the question, can you kind of tell what's going to happen in these combinators? And sometimes it's really hard. Like, let's say here's one. This is just a size. This is a size 9 combinator expression. That's it running for 10,000 steps. We can keep it going. That's it running for. Oh, sorry. That was a different one. Sorry. This is one running for 1,000 steps, same size. The question is, what is this going to do? Let's run it now for 10,000 steps. That's what it does. Okay. We say what's going to happen next. That's what it does. We keep running it. We keep running it. There it is for 100,000 steps. Still not clear what it's going to do. There it is finally for 100 million steps. And it turns out this particular combinator expression after 137,356,329 steps finally stops. So this is something where if we were going to try to predict what this is going to do, we would realize that this is very difficult. And this is kind of a sign of a feature of combinators that they're capable of doing universal computation. And what we're seeing is kind of the sign of undecidability, the sign of the undecidability of the halting problem for combinators. Well, one thing I might say is, should it surprise us that these very simple rules can produce such complicated behavior? Should it surprise us, and should we care? We might say, why did we build combinators? We built combinators to do useful mathematical logic. We built combinators to do computations that that we kind of care about setting up. Why do we care about what combinators in the wild do? Why do we care about this kind of natural history of combinators? Well, it's not clear that in the past one would particularly have cared. My own efforts actually probably tell one a reason one might care. Basically, the question that I started thinking about maybe 40-something years ago is the question of, if you want to make models of things that happen, for example, in nature, what is the right raw material to make those models out of? And we've had, for about 300 years, we had kind of the mathematical equations approach to having a way to make models for things. And that approach was obviously very successful. But the question was, particularly when we see really complicated phenomena, for example, in nature, the question is, what is the right raw material from which to make models of those kinds of things? And what I kind of realized is, actually, we want to be more general than just using mathematical equations. We want to use sort of arbitrary kinds of rules to represent the kinds of things that nature potentially can do to produce the kinds of behavior it does. And so that got me into thinking, well, how would we represent those kinds of rules? Well, the obvious thing to do is use programs. then the question is, okay, so what kinds of programs might nature be using to produce the kind of behavior it produces? And so that got me into many years of kind of study of these kinds of things. I was sort of lucky in that the first type of systems that I studied along these lines were cellular automata, one-dimensional cellular automata, where the state of the system is represented just by a line of black and white cells. And all you're doing is saying, here's the rule for the system. And then you're saying, how does the system produce its behavior based on that rule? And these systems have the nice feature that you can kind of visually immediately see what's going on. And so I did a bunch of computer experiments long ago to find out when you have these very simple rules for, in this case, one-dimensional cellular automata, what do they actually do? And my first assumption was, if the rule is sufficiently simple, the behavior is going to be somehow correspondingly simple. But then, you start seeing examples like this, you keep running it a bit longer, you get things like that. But then kind of the big thing is you just run all possible rules of that simple type that I was showing you. And this is kind of my all-time favorite science discovery, is this thing that I call Rule 30, which is just this very simple rule for a cellular automaton. You started off from just one black cell at the top here, and this is what it makes. Keep running it a bit longer, this is what you get. There's a certain amount of regularity over on the left, but for many practical purposes, this seems to be producing quite random behavior. In fact, the center column here is a really good random number generator that we've used for many years. So the big surprise is, contrary to what one's intuition might suggest, even things with very simple rules that you might sort of just pick at random can produce incredibly complicated behavior. Why is that important? Well, one reason it's important is because what we see in nature is the same kind of thing, that even though in many cases we know that the rules for systems are quite simple, the behavior those systems produce is very complicated. And there's sort of in this question, what's the sort of secret that nature is using to make all that complexity? And I think we now know what that is. It's basically that in this sort of computational universe of possible programs, it's actually very easy to have even very simple programs produce behavior of great complexity. Now, we hadn't really seen that for two reasons. One, because when we do engineering, we want to set things up so that the thing we build will be something whose behavior we can readily foresee. That's often been the point of engineering. That's one reason. The other reason is that with the methods of mathematics and things like this, we tended to concentrate, for example, not on the randomness of the primes, but rather on those features of the distribution of primes that our mathematical methods and theorems and so on could attack. And so this kind of, let's look at the sort of raw complexity of what can happen, even with simple rules, wasn't something that people had studied. But it's something that's out there, and it's something that's really important if one wants to understand things like the natural world. Actually, a thing that's been really significant to me to see over the past probably 20 years or so, this transition from something where for like 300 years, when people made models of things, they basically turned to equations to do that. In probably the last couple of decades, when people have made new models of things, they don't turn to equations, they typically turn to programs, and they make their models using programs. And what we're studying here is kind of the basic science of that process, of what is the basic science of what sort of programs out in the computational universe actually do. And so there's a lot to understand there, and there are some general principles about what programs out in the computational universe typically do. The biggest is this thing I call the principle of computational equivalence, which is kind of an intuitive principle, a bit like the second law of thermodynamics, to which it is deeply related, which it actually implies. It kind of gives us a sort of guiding principle for understanding what happens in the computational universe. And one of the things that, why am I talking about all of this? Well, the reason I'm talking about all of this is because combinators are, and in a sense were, a fantastic example of this phenomenon. The combinators, even though all these things that I was showing you about kind of the zoology of combinators, that's really this story of how in the computational universe of simple programs, how you can get extreme complexity of behavior. Now, what we found most recently is having realized that, yes, it's possible to go from extremely simple programs to very complicated behavior. Kind of the big thing that one might think about then is, well, what about our whole physical universe, for example? Is it conceivable that somehow the structure of our whole physical universe is just a feature of some very simple rules like that? And indeed, rather excitingly, just in this past year, we've discovered that, yes, actually, it really is true that, in a sense, something which that it's possible to understand what sort of underneath space and time and so on, to actually sort of find the machine code for the universe. And it's really quite a remarkable thing. And it's something where this sort of notion that one can have a simple program and have it actually show behavior that is sort of as complicated as anything. We now really know that that's the case because we really can understand how that works in physics. And the thing that's remarkable is that from just these very simple programs, we've discovered that it's possible to reproduce this sort of, particularly the two main theories of 20th century physics, general relativity and quantum mechanics. Now, one of the things that that is sort of surprising about physics is that it's sort of possible to do physics. It might be the case that you would look at something like that Rule 30 cellular automaton and you would say, gosh, it's very hard to predict what that's going to do. In fact, that principle of computational equivalence that I mentioned implies this phenomenon of computational irreducibility that basically says, to know what this is going to do, you pretty much have no choice. You can't do something much more efficient than just running it and seeing what will happen. You can't kind of do what traditional equations-based science has considered so valuable, to sort of jump ahead and compress the sort of computational effort of figuring out what this is going to do. So one big question about physics is, okay, how come we can do physics at all? How come the universe doesn't just seem to us this incoherent mess of computational irreducibility? And I have to say that when I started thinking about how the physics might be based on very simple programs, that's kind of what I assumed was going to happen, that we would only be able to figure out what the first 10 to the minus 1,000 seconds in the behavior of the universe were and so on. But it turns out that that isn't the case. It turns out that within this kind of computational irreducibility, there are these kind of slices of computational reducibility. There are these ways in which, even though the structure that we get at the lowest level has this whole feature of computational irreducibility, there are ways to kind of take slices of that are easier to understand. And it turns out the two big slices we can take are relativity and quantum mechanics, and they're deeply related to each other. In fact, in some sense, they're the same theory. Now, why am I telling you this? Well, the theory that we have for physics is not combinators, but the theory we have for physics is deeply related to a lot of the kinds of things that we can understand from combinators. And a lot of the mathematical development of combinators and things that came from them are the things which, in the end, give us things like the validity of relativity, features of quantum measurement, all those kinds of things. So things that come out of the theory of term rewriting, theory of all sorts of things related to combinators turn out now to have a big application. And the big application is kind of the biggest thing we have, our universe actually understanding fundamental physics. I might just mention that when we talk about combinators, we can think about combinators as being, how do we think about a combinator? Well, a combinator is this symbolic expression, and we can kind of represent that symbolic expression as a tree like this. So this is just like I was showing those expressions from Wolfram language at the beginning. This is just a combinator expression shown as a tree. And so when we think about the evolution of combinators, what we're essentially doing is thinking about the evolution of trees. What we've got with combinators are, we've got these rules that, it's a bug there. We've got these rules that basically tell us how to rewrite pieces of trees. And so whenever we're looking at one of these pieces of combinator evolution, we can think of them as being a process of rewriting trees. Well, when we, in our models of physics, what happens is that we have something very similar, not quite the same, very similar that's happening. Instead of thinking about trees, we're thinking about hypergraphs. And what we're imagining is that what is our universe made of? our universe, well, since Euclid, people have sort of assumed that our universe is just has space in it and things can be placed in space. But what we're thinking about in our model of physics is what's underneath that. What is space itself made of? It's kind of like you could ask, what's a material like water made of? And you would realize that in the end, water is not just this continuous fluid that you might think it was, but instead it's made of discrete molecules. And so what we imagine is that the same kind of thing is true of space, and that ultimately there are these kind of atoms of space. And these atoms of space, they have no characteristics other than that they exist, and they're just these sort of points in space. And the only thing we know about them is how they're related to other points. And so instead of drawing a tree, we're going to draw a graph or a hypergraph. And instead of having one of those combinator relations, we're going to have a relation that says, this is how we're going to rewrite pieces of that hypergraph. Okay, so if we do that, let's say we start with a hypergraph that looks like this, and we rewrite it a bit, we will get something that looks like this. We keep going for a while, we'll get something that looks like this. It's very much the same kind of thing that we saw in cellular automata. It's very much the same kind of thing that we saw in combinators, but now it happens to be in hypergraphs. What happens with these hypergraphs? Well, you can get all kinds of exotic things produced, but one of the things that happens is, here's an example of one that kind of knits this structure. You look at that structure is like a two-dimensional grid. So essentially this thing is knitting something like two-dimensional space. And so it turns out you can have other rewriting rules that knit things like curved space and so on. And the big thing is that just like you can go from kind of the discrete behavior of molecules in water, you can kind of zoom up to see what the fluid equations are for water as a continuous fluid. So you can do the same kind of thing from these underlying models. You can find out what is the kind of zoomed up version, what's the kind of large scale structure of a system like this when it has perhaps 10 to the 400 points in it. And the answer is the remarkable answer is that it is exactly Einstein's equations, that it exactly gives us the standard equations for space-time that come from quite generically from the kind of large-scale behavior of these kinds of systems. Much like in fluid dynamics, it ultimately doesn't matter that much what the underlying molecules are like. The large-scale behavior is always the same. That's actually a consequence also of this computational irreducibility phenomenon that I mentioned earlier. All right, well, let me not talk in detail about physics, but let me just say that's by way of motivation of why, even more than before, I care about combinators now, because it turns out that the ideas that came from combinators are deeply related to the kinds of things one needs in physics. Okay, so one of the things to say about combinators, and we can represent these combinators in all sorts of ways. We can kind of make them look a bit like a cellular automaton here, just writing out their Ks and Ss and so on like that. We can make nice 3D pictures of them that show kind of the size of the combinator as a function of number of steps and so on. You can do all kinds of things like that. It's pretty hard to understand how combinators work. This is a picture showing the size of a combinator expression, and that's showing where the combinator expression got rewritten, where the actual update rule that said S of XYZ goes to whatever was applied. Okay. Well, now let me add even more complexity to this situation. So the issue is where are the updates actually going to get applied? By the way, in terms of looking at sort of how combinators behave, another thing one can do is one can say, well, when we build these trees, they're kind of inefficient because in a sense, a lot of subtrees are the same in these trees. And so in sort of a computer sciencey way, we can turn that into a DAG, and we can ask, what is the evolution of combinators in terms of DAGs? And you get things like this. And no, it's not easier to understand what's going on in terms of these DAGs where we kind of shared all possible common sub-expressions than it is in the original tree form. At least it isn't easier for me. Okay, well, so the next big question is, if you have a combinator expression, let's say you have this expression here, you can see that there are a variety of places. The red pieces here mark where the S rule applies. The blue pieces mark where the K rule applies. So one of the features of this is there are multiple different places where these rules can apply. So one of the questions is, if you're given a combinator expression, you're told, what does this combinator expression turn into? How does it evolve? What you realize is that there are many possible ways that you can go. There are many possible paths you can take. And in fact, there's a whole, you can start characterizing those different possible ways So for example, and one feature, one important fact is that if the combinator expression is going to terminate, then it doesn't matter what path you followed. You'll always get the same result. So there are a variety of different, you can think about a variety of different evaluation rules that you can use. Here are some examples of different kinds of rules you can use for what do you evaluate first. I have to say that as a designer of computational languages, I've been very interested in trying to see whether one can parameterize these kinds of evaluation orders in a way that's actually useful for people. I tried back in my system called SMP back in the 1979, I tried to make a sort of parameterization of this. I don't think anybody, including me, ever understood how to use that parameterization. In Wolfram language, we end up with just basically two cases. Either you you evaluate things by going to the innermost depth first thing first, or you hold the arguments of a function and you kind of evaluate everything in one gulp, which is essentially leftmost, outermost. But there are a variety of different kinds of possible evaluation orders that you can use. Okay, again, why do we care? Well, there's a lot of importance to this in the theory of combinators, but for physics, there's a very good reason we care. This business about being able to take all these possible paths, that is quantum mechanics. The version that we understood in combinators is a very early version of that, but it's the same phenomenon as the phenomenon that leads to quantum mechanics. In classical mechanics, we kind of have this idea that sort of definite things happen. There's a definite path that things follow. In quantum mechanics, we have the idea that sort of all possible paths are followed, and we only get to know certain amplitudes of different things that happen. Well, the reason that happens is because in our hypergraphs, for example, just like in combinators, there are many possible evaluation orders. There are many possible different updates that can be made. And in a sense, we're following all those possible updates. And one of the big mysteries of quantum mechanics is, so if there are all these possible things that can happen, why do any of us think that any definite things happen at all? Well, the answer turns out to be the same reason that when you evaluate combinator expressions, it doesn't matter what path you follow. If they terminate, at least you'll always get the same answer. That phenomenon is the same phenomenon as the phenomenon that leads to essentially objective reality in quantum mechanics. It also happens to be the same phenomenon that leads to relativistic invariance, that leads to the fact that you kind of experience the same physics regardless of what reference frame you're in space-time. Okay, let's see how we can understand some of that. So one of the questions is, if we have a combinator expression and we say, we can rewrite that combinator expression in a variety of different ways. We can choose a different place, a different match for the rules and use those different possible matches. So this is now a graph that we can get. We call these multi-way graphs that show what the possible rewrites can be. And in this particular case, what we're seeing is we start off with this combinator expression here. There are two possible rewrites at the beginning. There are various different things that happen, but all paths lead to the same result. They all lead to the same fixed point. They're all, and this is, and so the key fact here, the so-called Church-Russell property or confluence, is that whenever there's a branch, there's also a merge. Now, there's a generalization of that we call causal invariance, which is relevant for things like the universe. The universe, so far as we know, doesn't halt. It doesn't stop. It doesn't get to a final result. It doesn't say the answer is 42 or anything. It just keeps going. And so it's a little bit more subtle what happens. And I will tell you, and this is kind of the big homework for some of the perhaps combinator experts here, is we don't quite know what the correct analog of causal invariance, as we have formulated it for hypergraphs and string rewrite systems, is for combinators. There undoubtedly is one, but we haven't got it quite right yet. Okay, so what happens with these combinator expressions? Well, let's take a look here. So this is, for example, a particular combinator expression, and it's just showing the size of the combinator expression, and it's showing eventually it reaches a fixed point. This is a multi-way graph that I'm showing here, and this particular path, this orange path, is probably the leftmost outermost evaluation strategy, which gives that result. But if we pick different strategies, so there's another example, we're showing that's a size 7 combinator expression. Eventually it ends up with a size 40 result. And this is a particular evaluation order, a particular path through this multi-way graph, a particular quantum history, effectively. So we can keep going. We can get much bigger versions of this. oops, that's we can look at. So these are sort of typical multi-way graphs. One thing we find is that in combinators, if they're going to come to a fixed point, there'll always be just one fixed point. But sometimes there'll be a combinator expression where there can be a fixed point with some evaluation order. That leftmost, outermost evaluation order will always find the fixed point if there is a fixed point. But there can also be ways to kind of get lost and just start generating bigger and bigger and bigger combinator expressions and never reach the fixed point. And you see that in the case of this multi-way graph by these orange things here are the things that are kind of still active. There's the fixed point down there that many paths reach, but some do not, and they kind of go and get lost. Now, for the universe, not getting lost is a very good thing because it means the universe keeps going. These fixed points, what do they correspond to in the universe? They correspond to space-like singularities in general relativity. They correspond to what happens at the center of, for example, a Schwarzschild black hole, where time basically stops, where all paths, if you're sucked into that black hole, all paths lead you to the singularity where basically time stops. The stopping of time corresponds to the arrival at a fixed point in a multi-way graph, a multi-way graph for hypergraphs rather than a multi-way graph for combinator expressions, but they basically look the same. So that's kind of the a thing that we see in that's one of the kinds of interesting features. And as I say, this idea of multi-way graphs is something that has been actually rediscovered in many different fields. In the study of combinators is usually called Bohm trees. I think they're called Bohm trees at least. Although I had some mail this morning from saying that maybe I'm wrong calling them that, but okay. These are multi-way graphs, at least as far as I'm concerned. Okay, well, we can ask questions about, one of the things we can do when we look at these multi-way graphs, one of the things that we learn from physics is the idea that one of the things that's important is not just to look at the kind of which combinator expression leads to what combinator expression, but also what the updating events were that led from one combinator expression to another. And in particular, here we're showing these are the actual updates that led from one expression to another. So there's an important question we can ask about those updates. And the question is, what is the causal dependence? What is the causal relationship between those updates? Why is that important? It's important because in physics, we observers are embedded inside the universe. We don't get to see the universe from the outside. We don't get to see all the kind of states of the universe from the outside. All we get to do is to say, we know what's happening to us. We can look out at the rest of the universe and we can sort of compare what's happening there to what's happening with us. And what that turns into is the statement that the only thing we're ever going to be sensitive to is the network of causal relationships between things in the universe. And so what happens is, in this case of this combinator evolution, what we're saying is what really matters is these updating events and the causal relationship between these updating events. What do I mean by that? What I mean by that is that when we do one of these updating events, in order to do an updating event, that certain inputs need to exist to allow that updating event to occur. And we can kind of trace what inputs need to exist for that updating event to occur. So for example, let's look at this. This is a string rewriting system, simpler than combinators. We're just saying there's a sequence of A's and B's, and we're just saying there's a particular rule that says how to rewrite the string based on saying, what does it say? It says BB goes to A, and it says A goes to BBB. And we're just using that here. And these yellow areas are the updating events that are applied to this string. Okay, so what we can ask now is, for this updating event here to be done, it has to be the case that this updating event here has already happened. No, this updating event here has already happened because we need that B there. So what this is, we can think of this as like, these updating events are like applying functions, and we need the input for a function to have been provided for the output from a previous function in order for that function to run. So we can essentially build a causal graph that represents the causal relationships between those updating events. Okay, so here's the causal graph for that particular case. Now, big fact, as soon as there is this property that paths converge, this causal invariance property, it implies that this causal network of which updating event depends on which updating event, you always get isomorphic causal, you always get the same causal graph. It doesn't matter what the microscopic updating order that you use is, you'll always get the same causal graph. And why does that matter? Well, one reason that matters, let me show you an example here, is we can look at, let's say, here's a string rewriting system. This is just one that sorts BA goes to AB, but we can say, let's do these updatings in a different order. Let's effectively pick a different reference frame, a different way of sampling what can happen in the system. Well, what does picking that different reference frame mean? We're basically picking a different kind of foliation of this. We're picking a different choice of what we mean by successive moments in time in the system. And it turns out that by picking that different reference frame here, we're essentially doing a boost, a relativistic transformation. And in fact, what we'll find even in the string rewriting system is that we will get Lorentz transformation. We'll find out that the string rewriting system obeys special relativity. It's a consequence of causal invariance that you get special relativity, that the reference frame, that the order of updating events that you use, essentially the evaluation order you use, the fact that the evaluation order doesn't matter is the same statement as the fact that the relativistic reference frame you use doesn't matter. It's also the same statement as the different quantum measurement approaches you can use give you the same result, or in other words, that there is an objective reality in quantum mechanics. So that's the that's what it means to that. That's why we might care about looking at this kind of network of causal relationships between updating events in combinators. And I'll just show you one or two things there. Let's see. That's a typical causal graph that represents the causal relationships between updating events in combinator expressions. This is actually a multi-way causal graph. So on top of that multi-way system that shows all the different possible branching paths for combinator evolution, this is showing the causal relationships between all of those paths. And things get really quite complicated quite quickly. But the main point is that there's a representation of these combinator evolutions in terms of causal graphs, just as there's a representation of the evolution of the physical universe in terms of causal graphs. That turns out to be the representation that we are sensitive to, and the fact that that's what we're sensitive to is what leads to relativity in quantum mechanics. Now we can ask questions about so you might ask, what's the detailed analogy between combinators and physics? Well, in physics, we can think about different events that happen and their relationships. So for example, there are time-like related events. There are time-like separated events. What does that mean? It means one event happens and that event in time can lead to another event. That's sort of a simple causal relationship between events. Another possibility in physics is that events are space-like separated. That means that we can essentially foliate this, the causal graph in such a way that we say that those two events are happening simultaneously in time. So that's saying that we've got this causal graph and we're drawing these foliations where the causal graph defines a partial order between events. It says what events have to have happened before some other event can happen. But what this is saying is there's a way of picking our notion of how time runs so that these events can be considered to happen simultaneously. These events can be considered to be laid out in space rather than in time. They're space-like separated. There doesn't seem to be a good analog of that in combinators, although maybe we just haven't found it. But that's a very important thing for the universe, that it's possible to have space-like separated events, that it's possible to have a meaningful notion of space. Okay, there's another type of event, there's another type of separation, and that's what happens in the multi-way graph. In the multi-way graph, okay, here's a multi-way graph with some foliations here. This one is sort of representing, this is a string rewrite system, it's kind of representing what happens in quantum mechanics with quantum observation frames. There's a kind of a second kind of separation between things. And that second kind of separation is what we can call branch-like separation. It's a separation where those things occur on different branches in the multi-way system. Okay, so what is branch-like separation? Branch-like separation is another kind of way that things in the universe can be separated from each other. And that kind of way is just like when we lay things out, we can think of things being laid out in time, in space. We can also think about things being laid out in what we call branchial space, in the space of possible branches. And that branchial space is kind of the slice across the multi-way graph. And that branchial space, I thought I had some pictures. Oh dear, where did they go? Yes, here we go. That branchial space is we take a multi-way graph and we foliate the multi-way graph. There are a variety of different foliations we can use. Those correspond to different relativistic reference frames or different quantum observation frames, different choices of quantum measurements. But in any case, we can take slices across here and we can ask, how are these states here related when by looking at, for example, their common ancestry in this multi-way graph. And so we can essentially draw the notion, and this is being drawn now for combinators. This is showing in a sense the branchial space of combinator expressions. This is showing how related are combinator expressions in a particular reference frame with respect to this multi-way graph. And things get quite complicated quite quickly, but this is branchial space. There's branchial space for combinators. We can draw branchial space also for the physical universe. Branchial space for the physical universe represents kind of a distribution of quantum states. This is showing essentially a map of the entanglement of quantum states in the case of the physical universe. And so there are all kinds of interesting phenomena, like just as there's a speed of light, which is a maximum speed in space, there's also a maximum entanglement speed in branchial space and so on. And sort of one of the big results of our physics project is that when we look in physical space at GD6, at shortest paths in physical space, the equations that govern kind of the paths of GD6 are the Einstein equations. And basically they say a geodesic is deflected by the presence of energy in the universe. So geodesic is deflected by the presence of energy or mass, and that's the force of gravity that's deflecting that geodesic. And so that comes out in our models from when we're just looking at ordinary space and at ordinary space derived from causal graphs and so on. What's the analog in branchial space? Okay, so we can also look at GD6 in the multi-way graph. We can look at GD6. We can look at the paths of GD6 in branchial space. And so one of the things that's kind of my favorite fact so far from our physics project is that the equations that tell you the deflection of GD6 in branchial space, those equations are related. They relate the presence of essentially quantum of energy in branchial space to the deflection of GD6 in branchial space. Those equations are the Feynman path integral of quantum mechanics. So it's kind of a remarkable thing that the Einstein equations in relativity are the same phenomenon as the path integral in quantum mechanics, just played out not in physical space. The quantum mechanics is played out in branchial space. And so question would be, what's the analog of that? What is the analog of quantum mechanics for combinators? How does that work? What can we say about the analog of the path integral and so on for combinators? And because they have the same idea of branchial space. Okay, well, actually combinators have one thing in addition that isn't in the physical universe. They have, not only do they have time-like separation, they don't really have space-like separation. Their space is pretty trivial. They're just full of black holes and other weird sort of deformations of space. They don't really have this notion of extended space in the way that hypergraphs do. They also have branch-like separation. That's what gives us this branchial space. Oh, I should have said, by the way, that the coordinatization of branchial space that I think is deeply related to a bunch of combinator of things that have been done with combinators. The coordinatization of branchial space is the story of how you actually get things like quantum phases in quantum mechanics. And it's very much the story of how quantum mechanics in detail works. By the way, one of the things that's also pretty nice about thinking about sort of physics at this, the machine code of physics is one way you can figure out whether you're right about how it works is you can essentially try and compile existing things to this machine code for physics. And we've been pretty successful recently in essentially compiling the standard formalism of quantum computing into kind of the machine code of these models based on hypergraph rewriting. Also compiling, Jonathan Gorard just got results just in the last few days showing actual black hole simulations based on our based on compiling things into this sort of low-level machine code of hypergraphs. Well, okay, so combinators have one twist that goes beyond what we see in physics. They have another form of separation that one might call tree-like separation. And so what happens in combinators is, in addition, do I have a picture of this? In addition to, that's a zoo of multi-way graphs for combinators. In addition to the separation that you get by having, maybe this is one, no. In addition to separation that you get in time, in space, in branch yield space, you also have tree-like separation where essentially one combinator form can be nested inside another combinator form. That's something which we don't have, I think, in the physical universe. There is a theory called scale relativity that kind of suggests that it sort of posits that kind of thing to exist in the physical universe, but I don't think that's really the way it works there. So, okay, that was a little bit of an introduction to combinators and why we care about them. Let me just mention a few more things about sort of the combinators in the wild, and then we'll talk about a little bit of the history of sort of how combinators have fitted into the history of mathematical logic and the history of computation, and then I'm going to talk about Moses Scheinfinkel. So one thing we can do, one sort of interesting direction, once we have this idea that we can kind of compile everything into combinators, we've got sort of this very simple basis for computation, we can start asking things like, can we understand things about computation just by compiling it into this very simple basis? For example, we could say, a thing people study is computational complexity theory, where we're asking, what is the fastest running program that computes a particular kind of thing? Well, when you have a very simple representation of programs, you can actually go ahead and start asking that question empirically. And I've done that for Turing machines and other kinds of things before, but let me show you some results for combinators. So these are memory time trade-offs for combinators. So these are basically showing when you're going to compute things, this is showing, I think this is time and that's memory. This is showing there are things that you compute, and sometimes there will be a more time efficient way to do it that uses more memory and the other way around, but this is kind of giving you sort of empirical computational complexity theory. We can then ask questions like, when you find the simplest program, when you find the smallest program that computes something, how does it do it? Does it have just one idea for doing it? Or does it have many different ideas for doing that computation? And so you can ask these questions about that this is a particular thing where these are the shortest programs that compute a particular thing. And it's kind of showing the different ideas that these programs use to do that computation. And you can do the same kind of thing. Not only can you deal with that with deterministic computations, you can also do that for non-deterministic computations using multi-way graphs. And multi-way graphs are kind of the story of non-determinism. They're kind of the representation of non-deterministic processes. Now, another question you can ask then is, let me see, what do I have here? So this kind of empirical computational complexity theory, you can also ask questions like, okay, if we're going to compute, those are just two examples of computing x of x. I think that's the multi-way graph that shows those computations and different paths through it. But one thing we can ask is, if we're going to compute, if we want to compute a particular thing, what is, for example, the shortest program that computes it? And for example, when we look at short programs, what can they actually compute? So this is for programs up to a certain size. This is showing what X expressions can those programs compute. And so we see that these are essentially the X expressions that are easy to compute, that have low algorithmic information content. They come from very small programs, but we can compute them. Remember that we might have thought that everything that comes from a small program must somehow be simple. But then we see things like Rule 30 or things like the things we've seen with combinators, and we realize that isn't true. In fact, it's probably not even true. Our whole universe is an example of something that probably comes from a simple program and presumably isn't so simple, or we shouldn't consider it that way. So, okay, we can ask these questions about what questions like, if we're trying to generate different kinds of numbers, what is the sort of what's the algorithmic complexity of generating different kinds of numbers? We can explicitly ask that for combinators. We can ask kind of what their sort of how they do with computational complexity theory. Now, one question we might ask is, when we're thinking about combinators and we're thinking about the fact that they can compute anything, well, we don't tend to use them as practical computers. Could we do that? One of the things could we, for example, could we make something, let's say, with molecules that actually implements combinators? I don't think it quite works with combinators, but I think things very much like that, it will be possible to do this with them. I mean, one of the things that's come out of my whole effort of my sort of new kind of science of exploring the computational universe is this idea that if you want to get computation, it's easier to get than you might possibly have imagined. And I've been on a hunt for many years now for sort of the simplest universal computers of various kinds. So for example, I mentioned that Rule 110 cellular automaton that's very simple. Let me show you, well, it's another example. Oh, I'm gonna have to type it in. Another example that we found is for Turing machines, we know this is the very simplest Turing machine that is universal. So I've been very interested in this question of what is the threshold of universality in different kinds of systems. For cellular automata, we know that the simplest cellular automata with just two states per cell and nearest neighbors gives universality. For Turing machines, it takes 2 states, 3 colors. That's the simplest possible universal Turing machine. The question is, it's taken a lot of work to find these simple examples of universality. The remarkable thing is that Moses Scheinfinkel found something that is really close, probably, to an absolutely minimal version of universal computation, but it was the first universal computation thing that was ever found. By the way, one question you might ask is, if you just look at just the S combinator, forget there even exists a K combinator. If you just think about the S combinator, what does it do? Can it itself on its own do really complicated things? The answer is yes. And in fact, I think it's even very possible that the S combinator alone is computation universal. One result, and I think we have the originator of that result here. Let's see if I have a nice picture of it. Oh, drat, I don't seem to. Let's see. I thought I had a nice picture of this. One result, due to Johannes Waldman from 2000, is that for S combinators, oh, I thought I had this picture. There is essentially a finite state machine, a tree automaton, that can basically take one of these combinator expressions and, yeah, here we go. That's a very bad version of it. And essentially evaluate. It can tell you from a combinator expression, it can tell you whether that combinator expression, if it involves just S's, is going to terminate or not. It can immediately tell you that by just essentially using this finite state machine. So just evaluate the tree, you can work out, is this thing going to halt or not? So in a sense, that's like saying for a cellular automaton, you can say, well, for rule 30, even though there's much we can't say about it, we can very easily say it's going to go out at maximal speed on each side. This is the same kind of thing. We can say this very fundamental fact about an S combinator expression, we can sort of immediately say, oh, it's not going to halt. The question is, within such expressions that don't halt, what happens? You know, when we first thought about computation, we thought about computation as you give input, grind, 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 you get output. It's kind of a thing where you get to a result where things halt. But in modern times, our computers we don't usually want them to just halt. Really, computation is a story of things that continuously happen, and we just have to sort of tap into that and get the results we want. And so the question is, can one do that for the pure S combinator? Can one actually find that that Schoenfinkel didn't even need a K combinator? An S combinator alone would have been enough to give universal computation. My guess is that that will work, and that there's sort of a harness that can be put on S combinators that will essentially let you run them to do any computation one wants. That's something that I will be surprised if that's not the case, because in sort of searching the computational universe for different kinds of systems, whenever the behavior of those systems doesn't seem sort of obviously trivial, it's turned out that those systems are capable of universal computation. And either there's some very basic mathematical facts that we could discover that would allow us to sort of unravel the complexity of S combinators, or they're going to be computation universal. Okay, well, so that was sort of a rather long description of combinators and why we care about them. I just wanted to say that in terms of thinking about sort of what the foundations of computation might be, we've been definitely going down. We've done the 1910 NAND Sheffer route for computation. That's how all our computers get made. We didn't do the combinator 1920 route. It's not clear whether we could instead do that. It's not clear whether when we start to build computers out of individual molecules, for example, whether in fact that isn't a good route to go. Those are interesting things to explore. I mean, I might say, just sort of in the big picture of kind of how we think about computation, one of the things that sort of my realization about the nature of computation is from what we see about very simple computational systems being able to produce such complexity of behavior, one of the things, and that we so easily get universal computation, one of the things we realize is that there's sort of this ocean of computational possibility that exists out there. The question for us as sort of humans wanting to use this is, how do we take the things that we want to do and map those things into this sort of ocean of computational possibility? And in a sense, the story of a lot of my life has been to try and design computational language that bridges that divide between what we humans like to think about and what's possible out in that sort of ocean of computational possibility. And that's I mean, what I've been trying to do is to kind of build that sort of notation that we can use. It's kind of the analog of the effort that people did 400 years ago to build kind of mathematical notation to kind of define how you talk about things mathematically. My interest has been to define kind of how you talk about things computationally, and to do that not just at the level of raw computation, not just at the level of what computers intrinsically do, but at the level of computation that we care about as humans, whether we're interested in geometry or graphs or things about movies or things about geography or whatever else, to essentially have a notation for computation that that bridges kind of what we humans care about to what is possible in the computational universe. That provides kind of the kind of notation that, in the case of mathematics, once mathematical notation was invented, people could invent algebra and calculus and so on. It's kind of the analog today is, once we have this kind of computational language, we can then really start to build the computational X fields and so on. So one of the things that, and so there's sort of a, one thing to mention about computational language design, it's all about kind of matching what humans can understand with what's possible in the computational universe. And one of the problems with combinators is they're pretty hard to understand. One of the features of combinators is you don't ever have to name variables. When you have a combinator, we have some combinator expression, it just tells you the tree is going to be built this way. The symbolic expression is going to be built this way. You don't have to say, well, I'm going to call one piece of the tree X, another piece Y, and so on and so on and so on. If we look at kind of what's happened in the history of combinators, kind of the core ideas of combinators and how they work, essentially all of those ideas have been well integrated into computation as we now practice it. The one that hasn't is this don't name anything. Now, of course, in human language, we're used to naming things. We have nouns, we have pronouns. It is very important to us as humans that we get to name things. We get to kind of give symbolic names to things in the world. But combinators don't do that. Combinators just have this kind of raw representation that just says you put all these pieces this way and this way and this way and this way, and then the whole thing assembles itself. They don't give names to things. So I've been very curious for a long time, is there a way that we can use that? Is there a way that people will understand that? Will people ever understand that? If we look at the history of kind of intellectual development, there are things that even 30 years ago, for example, I couldn't have put into a computational language because people just didn't understand those things. But gradually there's enough ambient understanding. There are words that get invented for things. People say, oh yes, I know what that means. You can then reason in terms of it. You can then put it into a computational language. there's a question of, is that going to be possible for combinators? We're at 100 years now, and combinators are not things that humans normally understand. Now, one thing I might say is that combinators, in a sense, they've taken this idea of symbolic expressions and they've kind of washed all the meaning out of them. When we write down a symbolic expression, it has a plus and a times and a this and that in it. We say there's a plus, there's a times. We know what those mean. But with combinators, we're kind of washing all of that out. And it's just a bunch of S's and K's. Is that useful? Is it useful to do that? Is it useful to have these kind of washed symbolic expressions that have nothing, they're just kind of the pure skeleton? Well, I have to say, I never really thought it was particularly. But then I realized that, well, I've spent my life basically building computational languages that are based on symbolic expressions. They're based on symbolic expressions where there are actual names for the elements in those symbolic expressions. Maybe in Wolfram language today, there are about 6,000 of these names that represent different kinds of things, whether it's geopositions or whether it's chemicals or whatever else. That idea, symbolic expressions with names, that's what's useful. But then I realized, as we're building this model for physics, I realized, in sort of an embarrassment for me, that these symbolic expressions that I've been using for 40 years, actually, the skeleton version of those basically is physics. In other words, if you take symbolic expressions and you you scrub out all of the actual meaning, and you just take the structure, and actually in the physics ones we're dealing with, they're just sort of two-level symbolic expressions that represent these hypergraphs, the life of those kinds of things seems to be physics. And so, in other words, it's like with combinators where we kind of, scrubbed out all the meaning. What do we have left? Well, we have combinators. The close analog of that for hypergraphs seems to be physics. So again, it's something where what Moses Scheinfinkel talked about 100 years ago was something where he's kind of scrubbing all the meaning out. And what do you get? Well, one of the things you seem to get is physics. Okay, let me talk a little bit. I'm running way over time, and maybe I should skip. I want to just give some kind of indication of kind of the historical arc of combinators and how they relate to other kinds of things that that sort of happened. I would say that the whole effort of Moses Scheinfinkel is part of a long arc of sort of representing things in a formal symbolic way. And I suppose one could trace the earliest examples of that to antiquity, to basically logic and geometry. Aristotle was cataloging animals and cataloging all kinds of things. And one of the things he wanted to catalog was arguments and forms of arguments. And that led him to basically come up with logic as a representation, as a disembodied symbolic representation of forms of arguments. And so many years went by, many things happened. But then by the time we got to, well, the 1800s, there's sort of a question that arose. People started realizing that there were things like logic had come out of sort of the actual arguments people make. Things like Euclidean geometry had come out at that time of the actual way that space seemed to work. I now think that the very first assumption of Euclid about the continuity of space is wrong, but be that as it may, it did very well to go from our perception of space to these sort of axiomatization of geometry. But so then what happened in the 1800s with group theory and then Lobachevsky's work on non-Euclidean geometry, and then transfinite numbers, things like that, was this idea that you could make up formal systems where you could say, these are the rules for the system. I don't know whether this corresponds to anything real, so to speak, but they're just these formal rules for a system, and I can go and work things out based on these formal rules. So one of the things that was needed when you started talking about formal rules, I mean, today when we talk about formal rules, we have a framework for talking about those. It's computation. When we say formal rules, that could be translated into essentially programs. But back in those days, there wasn't any such translation. People didn't know that. And so there's a question of how would you represent these formal rules? And that was partly a story of mathematical notation, partly the story of sort of developing a way to represent formal rules. And so, sort of a big piece of progress in that. There were a variety of different steps. People like Leibniz were involved in it. Other people, Frege, 1879. His oh, I can never say this. Begriffsschrift, his kind of concept script which was kind of a way of writing down what we would now call predicate logic, things with quantifiers and so on. He had this rather elaborate graphical notation, which I kind of wonder whether it's actually might be useful in modern times, now that it's really easy to have sort of graphical input for things and so on. I don't know. But in any case, he had kind of an effort to sort of represent everything in terms of predicate logic with this kind of script. Then let's see, I think this is Piano probably. Piano developed a kind of a similar formalization. He just, for good measure, he actually developed his own natural language based on Latin that was going to be used to represent the textual parts of things as well as the notation for the mathematical part. But kind of the idea was, let's take sort of everything we can talk about in mathematics and find a notational way to represent that. And sort of a big, at least a big sort of PR stunt of that was in 1910, Whitehead and Russell started publishing their ultimately 2,000-page Principia Mathematica book, where they wanted to show that basically all the things we normally talk about in mathematics could be reduced to and notated in terms of the concepts of logic. And they were very proud of, I think it takes them until page 400 or something to talk about the number 2 and so on. This stuff is very hard to read. I think it's actually a great example of really bad language design. There are just many, many, many things wrong with it that sort of a modern language designer can look at it and say, that was just the wrong way to do it. But in any case, it was in its time, it was very influential in giving people the idea that maybe one could build sort of everything in mathematics just from logic. Maybe one could represent everything in mathematics from the constructs of logic, and maybe one could build up all the ideas of mathematics that way. And one person who was very interested in related things was David Hilbert. So in the 1890s, he'd started thinking about, okay, given the Euclidean geometry, Euclid had certain informal axioms for things. Is there a way to kind of tighten that up? By the way, I recently just did a big study of sort of the empirical metamathematics of Euclid. That's the axiom network of Euclid. He has 10 axioms, 465 theorems that are proved, and that's kind of the network of what gets proved from what. In a sense, we can think of, by the way, these multi-way graphs as like metamathematical space. They are the space of all possible theorems that can be proved. And that's kind of the underlying space. Then what somebody like Euclid gets to do is to say, from that underlying metamathematical space, where should we humans populate? Which of all the possible theorems that we could prove, which ones should we care about? What is the geography as opposed to the geometry of metamathematical space? And that's just an example of kind of a simple empirical metamathematics. This is one for, I think that one's probably for metamath. That one is for lean. Those are just the proofs of the Pythagorean theorem in those systems. But these are kind of representations of kind of metamathematical space. But so, Hilbert was interested in this question of sort of how can you tighten up the axioms of geometry? How can you really make sure that just as a formal mechanical process, you can go from the axioms to just grind out the theorems that Euclid had, or in fact, in general, all possible theorems of geometry. So Hilbert was interested in that. In 1900, he starts giving his big list of problems and so on. Then, for about 20 years, Hilbert kind of lost interest in those kinds of things. And instead, he got interested in something very close to my interest. He got interested in the foundations of physics. He got interested in wondering whether, in fact, just as one had been able to sort of mechanize and figure out there are these axioms that make mathematics, can we similarly axiomatize physics? And actually, the thing he was most interested in was, can we go from an atomistic description of nature to the continuum? And that turns out to be exactly what we need for our current theory of physics. And it's kind of amusing that in Hilbert's 23 problems or something that he gave in 1900, some of those problems have fallen to undecidability, like Hilbert's 10th problem and so on. It's turned out that he said, prove this, do this, and it's turned out that's just not doable. Because of undecidability, because of essentially the sort of infinite consequences of computational irreducibility. Well, I think it was Hilbert's 6th problem was find an axiomatization of physics. And I think we can think of our project as, in a sense, an effort to do that. And that problem is going to fall the same way to computational irreducibility and undecidability as a bunch of other Hilbert's other problems. So it's just a funny footnote to these kinds of things. But anyway, so for many years, Hilbert was mostly interested in the foundations of physics. Then towards the end of the 1910s, he got interested again in the foundations of mathematics. And there was at that point with Whitehead and Russell and so on, there was a sort of big push to find, can we find the simplest foundations for everything? And so, for example, even when Whitehead and Russell heard about Scheffer's results about about NAND, they said, oh, we can, in the second edition, they kind of say, oh, we can actually make our logic even simpler by doing this. I might say that when you're dealing with NAND logic, one of my little achievements in life was finding the very simplest axiom system. It turns out to be a single axiom for Boolean algebra in the case of NAND. That's the result. And there's I found this in 2000. There's a giant proof of it that you can now just do in Wolfram language. It takes a few seconds, and you can kind of see what the network of lemmas is that makes it. But this is kind of a minimalized version of kind of what you would need to launch some of the things that were, for example, in Principia Mathematica. But in any case, so that was kind of the setup. Was at the time Hilbert had gotten interested in gotten reinterested in these kind of foundations of mathematics, and had this kind of idea that you could, if you could represent mathematics in some very simple form, then and get all of its axioms, you could then just sort of grind out all the true theorems of mathematics. Not everybody, it's okay. Well, Moses Scheinfinkel, as we'll talk about, was in Göttingen and was deeply influenced by what Hilbert was trying to do, by Hilbert's sort of program of can you turn all mathematics into axioms and then just grind out the results of mathematics. And so in a sense, what he did was came out of that tradition. He was attempting to sort of do the minimal version of that Hilbert program. What is the very simplest kind of foundation which one can build this out of? Let me just sort of skip ahead here. By the way, I might say that I posted today 3 rather large essays about combinators. I had started a couple of months ago thinking, oh, I should write down some sort of centennial thoughts about combinators. They got a bit long. It's probably about 300 pages now there. But so both about sort of combinators in the wild and about the significance of combinators and about the history of Moses Scheinfinkel. But let me just say that kind of sort of what happened with combinators. Let me just mention it, make a few comments. So I'll talk about in kind of the history of combinators after Moses Scheinfinkel gave his talk. Basically, nothing happened. Nobody referred to these things. Nobody cared until a chap called Haskell Curry discovered Scheinfinkel's paper. He had been thinking about similar kinds of things. I'll talk about exactly what he thought about and how it related to Scheinfinkel later. But he kind of launched this effort to really understand combinators and understand them as a sort of combinatory logic. Some of the people who are here were students or grand students of Curry's, and that was kind of the big push for combinators. I think the thing, a large part of what was being done there was an attempt to sort of mathematicize combinators, an attempt to sort of turn them into something more algebraic, more controllable by standard mathematics. They're actually very computational creatures. That's actually really hard to do. What was done, though, was slicing through various aspects of what combinators do. And what I think is interesting and very significant is some of those slices turn out to be exactly the same slices that we're now finding are relevant for physics. They're the things that make physics possible, basically. And I don't think we're done with mining what one can learn from those efforts with things like combinators to understand things in physics. And by the way, things in physics inform new ways to think about the kinds of things one's thought about in the case of combinators. But let me talk a little bit more about a couple of things here. So first question is this idea of computation. So in combinators, we had combinators were just this thing that in a sense seemed almost notational. Is there a way of representing these expressions of mathematical logic? Is there a way of sort of having mathematical logic work just through something simple like that? Well, then the question came up, how does that, how general is that idea? So, Hilbert's program of let's just find the axioms and grind out the theorems, the big thing that went wrong with that was Gödel's theorem. Let's see, is this the right page? Yes, there's the right page. And so Gödel's theorem, which arrived in 1931, basically the one way to think about what Gödel did is he showed that it's possible to basically compile anything into arithmetic. So people had thought about, in a sense, Schoenfinkel was one direction of how can you build up everything in mathematical logic? Another direction had to do with recursive functions. Fibonacci had his in the 1200 had an example of a recursive function. Even before that, there were examples of the Fibonacci function. But it was known in the 1920s, there was a whole bunch of study of recursive functions. People at first thought maybe the primitive recursive functions will be all that was needed to represent all reasonable functions. Then along came the Ackermann function, I think it was 1936, that shows that that's not the case. But the idea that you could sort of represent all reasonable things in terms of recursive functions, that was kind of a notion, one of the possible sort of foundations you could use for mathematics. The thing that Gödel did was to show that lots of mathematics and lots of things that you might have thought of were meta-mathematics, like statements like this statement is unprovable, that things like that could be compiled into pure arithmetic, that they could be turned into statements about factorials and equations with integers and things like this. And that fact was what showed that undecidability was a thing in mathematics and so on. But in a sense, what was done was, it was saying you can take all this stuff in mathematics, you can just compile it down to simple arithmetic. And Gödel also used general recursive functions. That was part of his sort of story. Now, for a while, I don't think anybody really understood what the significance of that was until basically about 1935, 1936, because that was when both Turing and Church did their thing. So what Turing did, so in fact, Turing, the title of Turing's paper, I don't seem to have it here, the title of Turing's paper was on computable numbers with an application to the, I'm going to translate into English because I can't say the German word, to the decision problem. So one of the things that Hilbert had defined as being sort of a key question in mathematics was this idea of a decision problem, this idea of could you decide whether some particular theorem was true or false? Could you always decide that? And what Turing did was he showed that you could have this construction of this machine that would have an undecidable decision problem, so to speak. And what he did was, in particular, to show that this Turing machine, this simple construction that he had, not nearly as simple as the Turing machine we have today, that minimal Turing machine that I showed you today, but he had the beginning of that road of a quite complicated universal Turing machine, which he showed had the property that with that one machine, you could reproduce the behavior of any other Turing machine. Of course, that's the thing that's led us to modern computing. It's the thing that told us that software is possible, that with a fixed piece of hardware, just by changing the software, you can do any computation. So that happened in 1936. Meanwhile, in 1935, Alonzo Church had come up with the idea of lambda calculus, and let me not go into this because I'm going to run out of time horribly. But basically, the idea of lambda calculus, it's what we call function in Wolfram language. It's it exists. It's now quite widely known in computing. But it's the idea of having an anonymous function, a function where you basically just say there are these variables, and the function can get applied to anything, and then you fill in these variables and get the result. Anyway, Church came up with that idea. Now, notice that when he came up with that idea, one of the things that was a big concern was, well, these variables, if we have a function of x and it gets applied to something, what if the thing it's applied to is also a function of x? How do we untangle this collision of variables? How does that all work? And is it even possible to untangle the collision of variables? Or will there be a bunch of paradoxes, maybe like some of the paradoxes of set theory and things like that, that will make it just impossible to untangle sort of conflicted variables. You know, in Wolfram language, if you try and input something that has these conflicted variables, something will turn red. But that's not something you can say, that's not the kind of level of thing that you need in mathematical logic. So when Church wondered, was it possible to untangle things in lambda calculus, what did he do? He had a footnote to Scheinfinkel saying, well, actually, you can turn these things from lambda calculus into combinators. You can compile lambda calculus into combinators. But then what happened was Church's paper came out just a little bit before Turing's, and Church was sort of trying to take what was kind of the more mathematical formula kind of approach to representing arbitrary things in mathematical logic. Turing took this more kind of mechanical approach. It was quickly determined that they were the same thing. It was quickly determined they were the same as recursive functions. Footnote, they were the same as combinators, but people didn't really care about that at that time. But the big thing that happened was all these different definitions of what it might mean to be computable, how you might construct things, they all turned out to be equivalent. And so that meant that there started to be this kind of robust notion of universal computation that existed. Now, at the time, people weren't sure how robust it was. You know, Gödel thought, oh, maybe, you know, human minds don't work the way that Gödel's sort of construction of things worked. People were very unsure, even up until the 1980s. When I started working on sort of applying ideas from computation to things like physics, people said, but of course, physics doesn't work like that. Physics involves real numbers. Physics involves computations that a Turing machine can't do in finite time. Physics is something different. The universe is different. These things that we've constructed in mathematical logic, they are just thought constructions of mathematical logic. They're not sort of things of physics. Well, I think that in the last year, we can now say that's not the case. It really is computation all the way down, and the things that were invented in 1920 by Scheinfinkel and later in the 1930s by other people that represent universal computation, they really are the way that our universe is constructed. They really are all we can get in concrete form in our universe. So in any case, so in the 1930s, the development developed this kind of notion of universal computation. Meanwhile, actual computers were getting built. You know, back in the 1830s, you know, people like, Charles Babbage had come up with his analytical engine idea, which I think Ada Lovelace understood much better than he did. But she kind of understood that you could weave, as she put it, algebraical patterns, as you can weave sort of pictures of birds and flowers with the kind of with a loom. She kind of understood that you could actually do sort of some kind of universal thing that is like computation with a fixed set of instructions. In that case, in the form that Babbage had specified for the analytical engine. But that idea was largely lost. And what happened in practice was that people built first mechanical computers and then later electromechanical computers. And there started to be, people had a unit that would do the addition, a unit that would do this, and they would chain these units together. Things got more and more complicated. By the 1940s, there was really the people were starting to say, well, we can sort of program these at some level. We can start saying how things are going to work. And there were a variety of kinds of ways that was done. Now, a little bit surprising is all this theoretical work, I don't think it had any relevance at all to any of that. That was done by physicists, electrical engineers, things like that, and they were just trying to make stuff work. They didn't really even know about these things done by Gödel and Turing and Scheinfinkel and all these kinds of things. But I mean, there was a little bit of kind of more formal stuff that was known. You know, Claude Shannon had shown that Boolean algebra could be used to understand switching circuits. That happened in the 1930s. Then things happened like there's a big emphasis in those days on kind of let's understand sort of, you know, there were complicated electrical machines. There were complicated machines in biology, like brains and like animals and so on. Let's try and bring these together. Things like cybernetics were kind of an idea to bring these together. And then 1943, McCulloch and Pitts wrote their paper on kind of a formal description of the nervous system that kind of pulled in ideas like Turing machines and so on to justify the idea that, oh, well, you know, we can have a nervous system that's just made of all these pieces that are like wires and so on, and it really can do everything. Turing machines sort of prove that, they kind of said. Well, kind of a link between these things was John von Neumann, who both had worked on set theory and things and had worked on mathematical logic, and also was an actual consultant for the people who were building actual electrical computers. And so he ended up writing these reports about sort of how you can be more formal about thinking about computers. And the initial versions of those reports talk about organs and all kinds of other very biological kinds of things. But pretty soon that's turned into talking about talking about things like Turing machines and Gödel's theorem and so on. Meanwhile, Alan Turing had gotten involved with computers and so on. And so there was kind of by I would say the beginning of the 1950s, I think, maybe there are people here who were around and can correct this, but by the beginning of the 1950s, I think there was a sort of a decent understanding that these computers made with electronics had something to do with the kind of idealized universal computers that people like Turing had talked about. And in the 1950s, there was kind of an explosion of interest in what would now be called the theory of computation. But most of the work that was done